Hey everyone, today we have this interesting trigonometric functions question. This is a paper 1 question, so no calculator, from the November 20 Math HL exam. So we have part A, which is a show that question, and it asks us to show that sine x times tan x divided by 1 minus cosine of x equals 1 plus 1 over cosine of x, under the condition that x is on the form 2n pi. And this condition just exists so that we're not dividing by 0 in this first bit here. And so we don't really need to consider this. We just need to work out the expression, how this first expression will get us to the second expression. In this case, if you look at the mark scheme, you'll actually notice that they allow you to go from the left hand to the right hand or the right hand to the left hand. It is shown as an acceptable method, but in general, you should try to go from left to right, because depending on the question, that might be all that's allowed. And so let's just start off with the equation. And one thing to always note is, even though you can't start with the right hand and go to the left, you can always look at the right hand side to see where you're going to end up. It's sort of a hint to you as to what journey you're going to take. And so what the right hand side is telling us is that we don't want to have any more sine x or tan x. We need to somehow get rid of those. And when you have a trig question, you know that you're going to be using some of the identities. And so over here on the right side, I just copied from the data booklets that you're going to have in the exam the identities that they give you. And so we have the identity for tan, the Pythagorean identity, and the double angle identities. And so you might notice that there's no double angle here or half angle at all. So we're probably not going to be using the double angle. So we only have two to really think about. And if you look at the first one, tan theta equals sine theta divided by cosine theta, this one looks useful because it gets rid of tan completely for us. And so let's just try to put this one into the equation. So we have sine x times sine x over cosine of x, which I just substituted in for tan x, divided by 1 minus cosine of x. And just by using some fraction rule, since we have a fraction in the numerator being multiplied, we can just bring this denominator down and just multiply this by this. So we have sine squared of x divided by cosine of x times 1 minus cosine of x. Let me just, my handwriting probably is not the clearest, so I'm just gonna try to make sure everyone can understand me. Now at this stage, you might get stuck and you might think, okay, let me just distribute the fraction at the bottom. This is technically a mistake. Now, I would do it too, so would, I think, most people, but it is a mistake in this case. But that's perfectly fine, because if at any point we do discover that we don't want to distribute it, we can just expand out. We can just factorize out the cosine x and go back to the old denominator, to the other expression. But even here, we're still stuck. There's really nothing we can do yet. And so what you might think to do is, since you see sine squared here, what your instinct might be to use the Pythagorean identity over here. The cosine squared plus sine squared equals 1. And that instinct would be absolutely correct. So let's just write this down here in red. Cosine squared, this is theta, not x, theta plus sine squared theta equals 1. But we want it in terms of sine squared, so we can put it in here. So if we just subtract both sides by cosine theta, we get the rule we're actually going to use, which is 1 minus cosine squared theta. Okay? And this is good, because now we get rid of the sine. Like we said in the beginning, we only want to have cosine by the end of it. And so if we just use this rule we will have our sign. We will have our desired effect. And so let's just put that in. Let's put in 1 minus cosine squared x times cosine x minus cosine squared of x. But again here, we did another substitution. We got closer, but we're still stuck. There's nothing, we have subtraction in the denominator. We can't really do anything at this stage. But there is something very nice that we can notice. And this nice thing to notice should be something you have memorized. This is a common property that's used in math questions over and over again, in trig questions specifically. And it's the fact that this form of the Pythagorean identity of 1 minus cosine squared of x is actually a difference of squares in disguise, because this 1 can just be written as 1 squared minus cosine squared, and that's a difference of squares. And just to remind those who have forgotten, because I do not believe this is in the data booklet, but a difference of squares, when you have a squared minus b squared, gives us a plus b times a minus b. And here you might see why we actually didn't want to expand in this stage. And so I'm just going to reverse that expansion. I could have just gone the whole way without distributing that, but that would be unrealistic. Like in the exam, you are probably going to distribute, and there are a lot of cases where you should be distributing. So, and simplifying in that case. So I decided to show you guys here that, you know, if you do that, it's not the end of the world. You can just go ahead and write it back here. Cosine x times 1 minus cosine of x. There, now everything is back the way it should be. And now for the difference of squares, we get 1 plus cosine of x and 1 minus cosine of x. And the reason we wanted to distribute over here is we have multiplication in the numerator and denominator, and we have the same term, the 1 minus cosine of x. So we can just cancel those out and be done with it. And we're basically done at this stage. We have 1 plus cosine of x over cosine of x, which we can just write out, distribute the denominator. We get 1 over cosine of x plus cosine of x divided by cosine of x, which this part just equals 1. And so we get our final answer in this box here, which is 1 plus 1 over cosine of x, which is what the question asked us to show in the beginning. And so, we got to that stage. We're happy with what we did for part A. Now, let's move on to part B. We don't really need to look at our work from part A, since we already have to show that. We already have what we need. I'm just going to put this here, and we're going to look at part B, which says, hence, determine the range of values for which sin x tan x over 1 minus cosine of x equals k has no real solutions. And so they've introduced a k here, mostly for the sake of the question. So first of all, this is a hence question, which means we're going to use the information from before. We have a range of values for k, and we want k to have no real solutions. Or, well, we don't want k to have no real solutions. We want the equation we have here to have no real solutions, and that basically means that x should have no real solutions, right? K is just a constant. K will have a real value, but at that real value, we want x to not be defined within the range of real numbers. That's our goal here. And so what this means is you have a quadratic or some other polynomial that doesn't have any real roots. That's the most common way, but in this case, since we're dealing with trig functions, what something having no real solutions means is that we're out of the range of the trig function. And so for example, for sine x and cosine x, the range is 1 to -1. If you don't remember that, just look at the graph. Actually, I'm going to draw this right here, since that's going to become very relevant in a moment. The graph of cosine of x, just going to look look like this. We're going to start at 1 from the top and then go down, and same thing in the other direction. Oop, that's probably going down a little too much. You know, the graph isn't very clean, but this range is 1 to -1. So we have 1 here and we have -1 here. So everything above 1 and everything below -1 is undefined for this expression. Okay, this is just some setup that you should keep in mind when you solve a question like this, and that you will need to know. This is some of the prior knowledge for solving a question like this. And first step is the hence step. It's using the information we gathered in part A, and in this case, thankfully, it's a very easy hence. It's just a substituting something at the very beginning, and so we can see the substitution. It's just turning this complicated expression into 1 plus 1 over cosine of x equals k. And so we want this to have no real solutions. Now this expression, which is an expression we can actually, deal with, do some algebra with, do some modeling with. And so in the mark scheme, there's one solution that tells you to just consider the graph of y equals 1 plus 1 over cosine x, which is also equal to 1 plus secant of x. Secant is just 1 over cosine. But in my opinion, this whole attempt is difficult. Not many people know the graph for secant of x, and then dealing with translations will make things very difficult. And so I'm just going to show you, if you want to do it this method, you can absolutely, and it'll work out just fine. But I'm going to show you the method that I think most people would use, and that's to rearrange this a little bit to get it to a form that we can actually use. And that form is basically being in terms of cosine of x or in terms of just x, because I think everyone knows how to deal with cosine. You should have this memorized. This is a paper 1 question, so you won't have your graphing calculator beside you, but you should know what the graph of cosine of x looks like, just as a piece of prior knowledge. So 1 over cosine of x equals k minus 1, which is protecting 1 from both sides, and then we can multiply by cosine of x and divide by k minus 1. It gives cosine of x equals 1 over k minus 1. And the mark scheme stops here, and that's perfectly fine. I would have probably gone ahead and done this other step, just found it purely in terms of x, which for any question like this, if you find it in terms of x, that's going to help you. So in this case, because cosine of x is very simple, you won't have any trouble dealing with it. But you could have gone like this, and it would have also worked. And so this is where knowing the range for cosine of x is important. For cosine of x to have a real solution, this whole thing will have to be between 1 and -1. But if we wanted to have no real solutions, which is what the question is asking, we know that, I'm just going to put this up top, 1 over k minus 1 has to be less than -1, or 1 over k minus 1 has to be, greater than 1, which is all nice and easy to understand. Now, some people might have the instinct to multiply both sides by k minus 1. But when you have an inequality and you're multiplying and dividing, you will have to be careful. Because if you remember the rules, you know that if you multiply or divide by a negative number, then you have to switch the equality, or the inequality, rather. And in this case, you don't know what k is. K is an unknown constant here. And so we can't use that method. And so the method you will actually use is to graph this. So with inequalities, looking at the graph is always helpful. And this is a rational function. It's a very simple rational function, actually. And you are expected to just be able to look at this and graph it. But let's go through and just analyze the features of the graph of this. 1 over, I'm going to use x here since we're graphing, 1 over x minus 1. So first of all, the graph of y equals 1 over x is just this, with asymptotes at y equals 0, horizontal, and then a vertical at x equals 0. But in this case, it's a little more complicated. We know we're still going to have both our asymptotes. They're going to be shifted slightly, and we might have some intercepts to deal with. So first of all, we can see there's no vertical translation. When it's in this form, when the x is only in the denominator, the vertical translation is going to be plus something here. But there's no, it's plus 0 here, so we know that the horizontal asymptote is not going to be effective. It's not going to go up, it's not going to go down. So we have 1 here, y equals 0. Next, the vertical asymptotes. The vertical asymptotes happen when, I'm just going to need to erase that plus sign that I left. But the vertical asymptotes happen when the denominator equals 0. And so that is x minus 1 equals 0, so x equals 1. And so we have our, oh boy, that's a very not straight line. When, yeah, x equals 1. And one other thing is that we do, in this case, have a y-intercept. So if we just sort of roughly graph it, we just do a sketch like this, we can see that at some point we are going to get this, right? This y-intercept. And the y-intercept happens when x equals 0. So if we just substitute x equals 0 into here, we get y equals 1 over negative 1, which is just negative 1. So we know this point is negative 1. But now we have our graph. I'm going to erase all this information that we gathered, just because it's not going to be necessary anymore. We already have it on the graph to analyze. This is usually not necessary to show to the examiners, since they if they see the graph, that's evidence of your work, and that is enough. You don't need to show them how you graphed it. It is expected that you be able to know this. Of course, I went through the long process. You know, most people would be able to look at this and just graph most things pretty quickly if they have experience with rational functions from before. But I just went the long way around just to help anyone who might be struggling with this. So especially with a type of question like this, you're using multiple areas of knowledge. You're using both functions and trig at the same time. You do have to be careful. And so it's good to sometimes go through this. But, you know, the important thing is we have our graph that we can analyze. And so what we want from this graph is for this right here to be less than negative 1 or greater than 1. And so, first of all, the greater than 1 is easy. So greater than 1 would be just everything that's here. So remember, first of all, we want the y to be greater than 1. It's very important. If we want the whole function to be greater than something, then we want the y value to be greater than that value. So since we want the whole of you know, this of the 1 over k minus 1 to be greater than 1, we want to look at the y values. And the y values that are greater than 1 is going to be here somewhere, right? And so let's just solve for whatever this line is for. So I don't think we need to draw a line. We should just, we know that there's going to be a point somewhere here with a coordinate of, you know, something 1. And we need to know what that something is. Okay? And so let's just solve for this. Let's just stop messing around on the graph and solve for it. And then we can see what effect it has on the graph. I'm just going to put this, you know what, I'll just put it over here. I'm just taking it out of here. So we want y to be 1. 1 equals 1 over x minus 1. You can just multiply both sides by x minus 1. In this case, this is fine because we have an equality, which is why it's useful to have a graph. We have x minus 1 equals 1, and so x equals 2. And so we have a line here of y equals 1. So this is not an asymptote line, to be clear, but it's still. And here, and the point is at 2, 1, this intersection point. And if we notice, for k to fulfill this inequality, for it to be greater than 1, then what we want is for the x value to be between 1 and 2. And since we're dealing with strictly greater than, we want to be strictly greater than 2 and strictly less than 1. Strictly greater than 1 and less than 2. And so the first thing we can get from the graph, the first actual inequality, is to get that k has to be in between 1 and 2. Okay? And then we want k to be less than -1. This part is actually easier. Since we already have -1 here, we already graphed it because it's an intercept. And so for it to be less than -1, again, remember, we want the y value to be under -1. We need to actually go greater. We need the x value to be greater than 0, right? Because at this point is 0, -1, but still below 1. So it has to be between 0 and 1. And so we also have here that k is between 0 and 1. And you can just combine these to get that k is between 0 and 2. And that is our final answer. That gives us the conditions for the inequality. And that inequality we got from the domain of cosine x, which is the function. And so we know the range of values for which, the range of values for k, for which this whole equation has no real solutions. This was not a very easy question, but if you just take your time, then you will be able to arrive at the solution. I hope this was clear, and thanks for watching.